All right. Okay, we started the day with astrophysics. We're going to start the afternoon with nuclear physics. Nuclear physics, am I up there? Yeah, nuclear physics in the age of the Earth. Well, like we started out this morning, solving a complicated equation, we'll start out this afternoon with an equally complicated equation, time-dependent Schrodinger equation, but we'll skip that. And I'm just going to review very quickly some of the same things about science that I talked about this morning because they're very important. That is, science is all about doing repeatable experiments. There are two kinds of science. Not all science is the same. Whoops, where are you going there, Turner? We've got physics and we've got cosmology. You remember this morning, physics is representative operational science where you're studying the dynamics of how the universe operates. It's all about what we can actually see and measure, and we can test it by repeatable experiments. And then you got sciences like cosmology, and incidentally, evolution fits in there, and the geology about establishing the history of the Earth fits in there. They're all the same sort of thing. That's historical science, and what you're doing is creating a story about history that tries to explain what we can currently see. And Richard went through a whole bunch of that with respect to the geological features of the Earth. And it was, he sort of illustrated that very well, that that's what you're trying to do. You've got all this evidence, and what caused the evidence? And the only thing that makes sense of all that evidence with respect to the Earth is the global flood. However, it's not testable by doing repeated experimentation, and it's open to a lot of speculation. All right, so we got to remember those things. Those are really important things to remember. So, how do we know how old something is? We're talking about the age of the Earth here, so how old do we generally know about something is? Well, typically we might think about appearance, right? People look old, right? So, for example, here is a desk. And if you go by the appearance of the desk, that's what's called a Louis XV desk, which means it was designed and built by and for the King of France around 1723 to 1774, which means the desk was built around 1760, so that would make it about 257 years old, right? However, you can actually have one of these made to order by a company in Arizona. It takes about 3 months. So you could have a Louis XV desk delivered to your house in 6 weeks or 9 weeks. And how old would it be? Right? Well, if you looked at it, it looked like it's 257 years old, but it was just made recently. All right, so appearance maybe isn't the best way. Another thing we could do is use a proxy. For example, here's a graph of height as a function of age. And so you can see that if you're this old, however old that is, I think it's 10, it's a little fuzzy, typically you would be about that high. So if you were to measure somebody whose height was that, you might conclude that they were that old. But you can see there's quite a spread. So they could be anywhere between that age and that age. Okay, so proxies aren't very good things for determining how old something is. The best thing is to have a written record attesting to its history. And you can actually get that with that Louis XV desk. The company that manufactures it will send you a certificate that said, this was made by us on this and this on such and such a day. Now, typically, we all have one of those things. It's a birth certificate. Right? The most reliable way to know how something how old something is to have a written record from a reliable witness or is recorded by a reliable scribe on behalf of the witness as to when something actually happened or when it started. Then you can know how old it is. In this case, the reliable witness is, or the reliable scribe, is the Registrar General of Ontario. Well, that's exactly what we have with Genesis regarding the origin of the history or the Earth or life on Earth. The witness is God. The scribe is generally considered to be Moses. Now, if you look at your birth certificate, you'll observe that the date in which the event actually gets recorded, the time at which it actually gets recorded, doesn't necessarily have to be the same date as when it happened. My birth didn't get recorded until 11 days later. And I didn't get actually my written record of that until many years later. So it's not necessary for all of the recording to be done exactly at the time that the event happened, as long as the, if you like, chain of knowledge or chain of evidence is reliable. Okay, so what does this reliable record that we have say about the age of the earth? Well, it goes through this kind of thing quite extensively. When Adam had lived 130 years, he became the father of a son and called him Seth, and Seth lived 105 years, blah, 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 blah. If you go through all of those, you can put together a picture like this, which is from the back of my Bible. And if you kind of work all of that out, eventually it ties into events that we know in recorded history, so we know when those happened, and we can figure out that the whole thing started about 6,000 years ago. So that's how old the Bible says the earth is. Now, if you were to Google the age of the earth, you'd get this, right? And if you were to click on, that's certainly not 6,000 years, if you were to click on the first thing that appears underneath that, which happens to be Wikipedia, wahoo, you get this. The age of the earth is. Notice that. That's a very definitive statement, right? Not is thought to be, or might be, or anything. It is. So it brooks no question, right? It just is. 4.54 plus or minus 0.05 billion years. That is 4.54 times 10 to the 9th plus or minus 1%. Ooh, wow. That's really accurate, isn't it? They really know what they're talking about. So how can we question that? Well, actually, that's not accuracy at all. It's repeatability. Here are two patterns, or two targets from a target shooting practice. Here's one shooter. Here's the other shooter. Now, you'll notice this one has a much bigger spread, more plus or minus to the pattern, than this one. That's a much tighter pattern. That shooter is much more repeatable. Didn't get them all in the same hole, but close. Much closer than the other one. But which one is more accurate? Right? Quite different things. Accuracy is the difference between the answer that you have and the right answer. And repeatability or precision is the dispersion in the number that you actually have, the answer the calculation that you did. Now, if you were to take these two patterns, which shooter is closer to the correct location? Which one is more accurate? Well, the fact is, you don't know, because you don't know where the bullseye is. Could be over here. Could be right underneath the close pattern, could be right underneath the spread pattern, could be anywhere. If you don't know the right answer, if you don't know where the bullseye is, you have no idea how accurate the shooter is. So this plus or minus, isn't accuracy, it's experimental repeatability. If they did those same experiments over and over and over and over and over again, with the same assumptions and the same equipment and the same calculations, they would expect to get numbers that ranged in that kind of variation. But that is not accuracy. Accuracy is the difference between the number that they quote and the true answer. And of course, we don't know what the true answer is, so how do we know how accurate this is? All right, then they say this age is based on evidence from radiometric dating. So we're going to have to talk about radiometric dating. So that brings up the question, does radiometric dating prove that the Earth is billions of years old? Well, short answer is no, because science can't prove anything to be true. That sounds a little counterintuitive, I'm sure, but it is nonetheless true, as evidenced by this exchange in Science magazine. This gentleman, who you can see, is got to qualify as a scientist, wrote this to as a letter to the editor. He said, the title of the 6 May News of the Week article, "At long last, Gravity Probe B satellite proves Einstein right," made me cringe. I find myself frequently repeating to students and the public that science does not prove theories. Scientific measurements can only disprove theories or be consistent with them. Any theory that is consistent with measurements could be disproved by a future measurement. I wouldn't have expected Science magazine, of all places, to say a theory was proved. Now, you could say, well, yeah, that's just his opinion. He's just ratting on. But, in fact, the editors of Science agree with him. He's correct. It's an important conceptual point, and we blew it. So just bear that in mind when you hear people saying science has proved something. Science can provide data that is consistent with a theory, and the more data that you get that is consistent with the theory, especially if you don't get any data that is not consistent with the theory, the more confidence it can give you that the theory is correct, like the theory of electromagnetism that Maxwell put together. Lots of experiments done. No data that's inconsistent with the theory. In fact, it was one of the foundation things for Einstein's theory of relativity. So we can assume that, for working purposes, Maxwell's equations work perfectly well. But that doesn't prove that they're right. All right, let's talk about radioactive decay then, because we're going to have to talk about radiometric dating. It's based on this decay process that a radioactive element decays to a stable element. The radioactive element is called the parent, and the stable element is called the daughter. Now, I like to say, I've had 2 daughters. They're now lovely young women. So I understand the radioactive parent thing pretty well. The stable daughter part, maybe not quite so well. But this happens with a half-life, which is the length of time that it takes half of the radioactive material that's there to transform into the stable element. So it looks like this. If we start out with 16 lumps of radioactive material, after one half-life, half of those, 8, will transform into the stable daughter, and so we're left with 8 radioactive elements. And then in the next half-life, this happens, and then the next half-life, this happens, and the next half-life, this happens. So you can see across the bottom, we have a count of how many lumps of each type of material that we can get. So we can do the ratio of daughter to parent, and we get these numbers. So these numbers, this ratio changes as a function of time. So you see after 3 half-lives, the ratio is 7. And we can actually plot this equation on a graph, and it looks like this. So after 3, or if you take 7 and put it on there, it'll tell you, if you measure 7 and put it on this graph, it'll tell you that the thing has been going on for 3 half-lives. So there are assumptions in doing this. One is that there is no daughter present at time 0, right? And we'll see what happens if that's not the case. The other assumption is that the rock is a closed system. That is, that over the lifetime since the rock was formed, neither any of the parent nor daughter have either been brought into the rock or removed from the rock by geological processes. Now, how are we supposed to know that? The other assumption is that the half-life has been constant. Now, the thing to notice about this is that if we're going to use this as a measurement tool, we should calibrate it, right? I mean, all measurement tools need to be calibrated. They've got people, that go around and calibrate scales in grocery stores and the pumps and gas pumps to make sure they are doing what they're supposed to do, that they're measuring exactly the same amount to do that. Now, calibration is the comparison of a measurement value delivered by a device, pump in the gas pump or those scales at the grocery store, with those of a calibration standard of known accuracy. And the calibration standards, in turn, are normally traceable to a national standard held by a national meteorological institute. A lot of these are held in a place in France. Now, there are no known calibration standards of known accuracy traceable to national standards held by national institutes for rocks being millions and billions of years of age. There just aren't. So radiometric dating is a completely uncalibrated instrument. The best that you can do is to use it to measure things where you know how old the thing is and see if it gets the right answer. So let's give that a try. Here are some of the decay schemes that are generally used for doing radiometric dating. This one is a particularly significant one because it is commonly used for measuring the age of volcanic rocks. And the reason for that is the argon part of it, argon-40, is a gas, so it's assumed that when the volcanic rock is hot and molten, that gas will be boiled out of the rock. So that when any argon-40 that you see in the rock is assumed to have occurred as a result of decay of potassium-40 after the rock solidified. All right, well, how well does this work? Well, in New Zealand, there's a volcano with a totally unpronounceable name that is known to have erupted at 3 times in the past. So here's some volcanic rocks whose age we know, so let's go get samples and send them away for measurement. So they did that, and here's the answers they got back. I like to look at them on graphs, so they look like this. See, they're kind of all over the place. And of course, the right answer is way down here. Now, scientists aren't dumb. They pretty quickly figured out that this kind of error is a result of that assumption about 0 daughter being present in the rock initially is wrong. Okay, so if we go back here, we'll put in a certain amount of argon-40 in the rock at the start. And then, of course, it just stays there all the way through. So that changes all of those ratios, or all those numbers at the bottom, which changes all the ratios. So now if we take the ratio 11, which is what's happening after 3 half-lives, put it on this graph, the age comes out to be quite a bit more than 3 half-lives. All right? So in this case, we know that this assumption about 0 daughter is wrong, because we know when the rocks were formed. But suppose somebody brought us a piece of volcanic rock, asked us to measure the age using potassium-40 dating. How would we know how much potassium-40 was in the rock to start with? Well, we wouldn't. So how would we know that the age that we got was right? Well, we wouldn't. So that suggests that this radiometric decay scheme isn't reliable for making measurements. So again, scientists sort of figured this out, and they said, well, we need a technique that will allow us to not make this assumption. So they developed one. It's called isochrone dating. So in addition, what required here is that in addition to this particular decay chain from parent to daughter, which I'm now going to refer to as the radiogenic daughter, that is the daughter that was produced by radioactive decay, there is another isotope of the same element at the end, same daughter element, that is naturally occurring. It's not formed by radioactive decay, and I call that the non-radiogenic sister. Now what they do is they make an assumption that what we'll do is we'll go around and we'll collect a number of different samples of what is ostensibly the same rock from different places. So these rocks may have different amounts. They have sort of formed slightly differently, so they may have different amounts of each of these elements in them to start with. But the assumption is the ratio of the sister to daughter is always the same. And that's based on the assumption that since they're the same element, they will have the same response chemically to anything that's going on. So you will get that same ratio in all of the rock samples. So then what they do is rather than measuring the ratio of daughter to parent, they measure the ratio of daughter to sister and parent to sister, because the sister is kind of constant, doesn't change. All right, so now, instead of these assumptions, we have a new one, which is that ratio of sister to daughter is the same in all the samples. And what they do is they measure those two ratios, plot them on a graph, and if everything works out right, you should get a straight line. And from the slope of that straight line, you can figure out the age, right? All right, so potassium-40 won't work, but it turns out all the rest of these decay chains will actually work with isometric dating. So we have rubidium to strontium, there's another strontium, we have samarium to neodymium, there's another neodymium. And in the case of lead, it looks like this, and instead of doing lead, the single lead to daughter, what they do is both of these ratios, and then they plot those two ratios against each other. So it's just a kind of a second order isochrone thing. And here are some results using the different approaches. And so you can see there's some pretty nice straight lines there, so everything seems to be working satisfactorily. If you use the data to calculate the age, you get these ages that you can see on there, and that plus and minus, that's the repeatability or the uncertainty. based on the uncertainty in the actual measurement. So you can see each of the measurements has a little vertical bar. That's the uncertainty in that measurement, and that'll determine what sort of certainty you can get in the slope calculation, and that's what's reflected in that plus or minus. So you can see them up here. They're all pretty good. All right, so that seems to work pretty well. So let's go try that on the rocks from the volcano in New Zealand. So now, instead of something around a million years, we get 133 million and 197 million. And if we incorporate the lead one too, we get now 4 billion years for this volcanic rock. So they're not agreeing very well. But somebody might say, oh, just a minute. Yes, potassium-40 is designed to try and measure the age since the rock solidified. But these other things, they could actually be measuring the rock or the age of the lava that formed the rock. Well, that's true. But if that's the case, they should all be the same because it's the same lava. And they're not. And they don't agree with each other within the stated uncertainties. And then we go back to these ones, which seem to have really nice fits and really low uncertainties. They're all actually for the same rock. And if you plot those on a graph, it looks like this. And these numbers that I've put in there, the 7 times 10 to the minus 3, that's the probability, based on the quoted uncertainties, that those two numbers could actually represent the same variable. They're the same age, right? So in one case, it's the probability is 2 times 10 to the minus 9th, 2 parts in a billion, that those two ages could be the same. Put it a different way, here we have some measurements taken with a micrometer of the thickness of a machine part. 124.0 plus or minus 0.84 millimeters. Yes, 0.84 is not very big, et cetera, et cetera. Okay. Which one of these is the right answer for the thickness of the machine part? I mean, they don't agree with each other at all. Which is the right one? Well, you don't know, right? Because you don't know what the right answer is. You're just measuring because you don't know. And so similarly, what's the right age for the rock? How can you know? They don't agree with each other, so it's quite possible none of them are the right age for the rock. So if we look back at this, it could be that this is a result of problems with this assumption, or problems with this assumption, or indeed problems with that assumption. I mean, they all seem like reasonable assumptions. But obviously something is wrong, because if not, the numbers would all be the same. And in fact, there were some experiments that demonstrated that the half-life, or conversely, the rate at which nuclear transformation occurs, is not constant. This one shows a variation, the one down here shows a variation of about 0.1%, and the other one about 1.8%, which is not big, but if your assumption is that they never change, and you see a change, then that suggests that the assumption may well not be right. Okay, so that one might not be right. It's also very hard to know for certain that the rock was a closed system, because there's a lot of geology going on in the past, or that the other ratio was constant. So in reality, when you look at the characteristics of whether the kind of the output of what's happening, and the fact that these things are totally uncalibrated, I find it really hard to put any credence in these radiometric dates at all, at least for these old ancient rocks. There's another radiometric dating technique called radiocarbon dating, which is sort of the same, but works a little bit differently. I mean, it works on the fact that we got a parent and daughter and all of that, and the parent is carbon-14, radioactive carbon, decays to nitrogen-14, which is stable. Now, carbon-14 is not naturally occurring in the atmosphere or on Earth, so it needs to be constructed in the atmosphere, manufactured in the atmosphere, and that happens when cosmic rays come into the atmosphere, collide in the atmosphere with nitrogen-14, and cause a whole bunch of nuclear reactions that eventually wind up forming carbon-14. Now, carbon-14 is just like carbon-12 chemically, so it combines with oxygen to form carbon dioxide, and carbon dioxide, of course, is plant food, so this radioactive carbon dioxide gets absorbed into plants, and incorporate it into their plant material, so that makes the plants radioactive. The plants get eaten by animals like cows and stuff, and so they incorporate the radioactive carbon dioxide or the radioactive carbon from the plants into their tissues, and they become radioactive. And then we eat our vegetables and our hamburgers and steaks and stuff. We incorporate that radioactive carbon into our tissues, and we become radioactive. That didn't seem to bother anybody. How about that? But it's the best excuse I ever heard of for not eating Brussels sprouts. They're radioactive. You want me to eat that stuff? Come on. Okay. So now what happens is, while these things are living, that the radioactive carbon that they've already absorbed is transforming back into nitrogen. But they continue to eat more stuff with radioactive carbon in it, so they're replacing it. So we build up an amount in our bodies, and it kind of stays more or less constant throughout our lives. But then when we die, or the plant dies, or the animal dies, that stops, right? So it has a certain amount of carbon-14 in its tissue at the time it dies, and it's decaying to nitrogen. So over one half-life, half of that will decay to nitrogen. And over another half-life, another half will decay to nitrogen, and so on and so on and so on. Now, the tissue, whatever it is, plant or animal tissue, will decompose, and the nitrogen will go back into the atmosphere. Right? So we can't use the same technique that we used before of measuring the ratio of daughter to parent, because the daughter is left home. But also in the tissue, there's carbon-12, which is the non-radioactive carbon, the stable carbon. So it doesn't change. So there's a certain amount at the time that the specimen dies, certain amount of carbon-14 in it, a certain amount of carbon-12 in it. The amount of carbon-12 doesn't change. The amount of carbon-14 changes, like this. So if we knew what the ratio was when it died, and we could measure the ratio what it was when we get the sample, and we knew what the half-life was, we could do some math and calculate how long this had probably been going on. Now, the assumption is that the ratio of carbon-14 to carbon-12 at the time the specimen dies is the same as it is in the atmosphere today. Sort of. That's not entirely quite correct, but start there, that it's the same as it is today. So that means that, things that were living in the past, they're just assuming that the ratio of radioactive carbon to non-radioactive carbon in the atmosphere has always been the same. And we can measure that, right? We can measure what it is in the atmosphere today. It's actually 1 atom of carbon-14 to every 1.2 trillion atoms of carbon-12, so it's not very big. That's what's referred to as moderate carbon. What they measure over here is percent moderate carbon, and they actually do measure the ratio. The machines that they use are set up so that they can simultaneously count the number of carbon-14 atoms that arrive at the detector and the number of carbon-12 atoms that arrive at the detector. So they're actually measuring the ratio, which is kind of cool. They're called accelerator mass spectrometers, and their sensitivity goes down to about 0.002% moderate carbon. And if you do the math, that corresponds to about 15.6 half-lives. Half-life of carbon-14 is 5,730 years, so 15.6% of them is about 90,000 years. So if there's a specimen is older than 90,000 years, then theoretically, there is insufficient carbon-14 in it for the best machines available today to detect it. Okay? So that's the upper limit at which they'll be able to measure ages. Now, you saw this picture earlier, and I recognize it's all wrong, Richard. I recognize it's all wrong, but this is what people say is supposedly the geological column and all the fossils it contains. And one of the things it contains is coal. Richard alluded to that, all the massive amounts of coal that had been buried, or vegetation that had been buried to make coal, and it actually occurs in pretty nearly every layer in the geological column. And in the U.S., the U.S. Bureau of Mines keeps samples of coal from all the different coal beds all around the country. So some scientists got some samples of this coal from 3 different layers that, according to the uniformitarian geologists, are quite old, millions of years, anywhere from 30 millions of years to 300 million years. That's certainly greater than 90,000 years, so there should be no detectable carbon-14 in these at all. Sent them away to an independent lab that does this kind of stuff, and this is what they got back. Lots of carbon-14. Right? Here's the limit of sensitivity, which corresponds to 90,000 years. These are the ages that would correspond to the amounts of carbon-14 actually measured. Remember, the alleged age is in the millions of years, and you actually measure an age of a few thousand years, like 50,000 years. Now, an interesting thing is, Richard was talking about dinosaur bones that are still bones, and the soft tissue that they have in them. They've sent dinosaur bones, scientists have sent dinosaur bones away to have carbon-14 dating done on them, and they come back with these, essentially the same. Right? Now, there are two things to notice here. One is there's no indication of any of the different layers from which the coal was derived, but they were vastly different, supposedly, in ages. So you'd think, if anything, you'd see one here, and one here. And the same with the dinosaur bones. You'd think they would correspond to one of those layers, right? But they don't. They all have essentially the same amount of carbon-14 in them. Now, there was some concern that maybe coal wasn't the best material to do this with, so they got some diamonds. Diamonds are a very hard form of carbon, impervious to any kind of ingress of contamination. They sent those away and got very similar results, right? Not quite as high as the other one, so a little bit older in age, but then these guys were supposedly billions of years old, not millions. And a third example of something unusual going on happened in Australia at a mining site where the cross-section through the soil looked like this. Okay, so there's a bunch of sand and clays. Down lower, there's a basalt layer, which is volcanic origin, which was considered to be of the order of 30 million years old. And then immediately below that, some other stuff that was supposedly 250 million years old. So obviously the basalt was an intrusion that came in on top of the other one with the sand on top of that. They sank a shaft down through this, and when they got to this point, they found some wood. It turned out to be a whole bunch of stumps, tree stumps. The roots of the tree stump were in the 250 million year old sandstone, and the top of the tree stumps, which were all charred, so they had been there when the basalt had come in and covered them up, were in the basalt, which was only, I can't remember now, a few million years old. So they took this wood, they took basalt and sent it away to be dated, and it came back as 45 million years old. They sent the wood away, and it came back to be 45,000 years old. But the wood was there when the basalt came in, right? So there's something not right here. Now, radiocarbon dating, remember I said, is based on the assumption that when the specimen was living, the ratio of carbon-14 to carbon-12 in the atmosphere was the same as it is today. So let's have a look at that and see whether or not that either stands up to evidence or is logical. So, and I'm going to look at three different points in time: at creation, at the flood, and today. We know what it is today, and let this represent the amount of carbon-14 in the atmosphere today. What about at creation? Well, I would suggest that at creation there was zero. Carbon-14 is not essential for life. Carbon-12 is the life component of carbon, so there was no reason for God to produce it. So that would mean it would be produced in the atmosphere the same way it is being produced today, which is by cosmic rays striking things in the upper atmosphere, causing nuclear reactions that result in carbon-14. So the rate at which that happens will depend on the cosmic ray flux, and the cosmic ray flux will in turn depend on the strength of the Earth's magnetic field. Because what the Earth's magnetic field does is actually protect us from cosmic rays. It causes the cosmic rays to be put back out. And the stronger the Earth's magnetic field, the more of those cosmic rays will be deflected back into space. We know from measurements that the Earth's magnetic field has been decreasing, at least in recent history, at about 5% per century. And if we draw a little graph of that, that means back about the time of the flood, it was 10 times stronger than it is today. And back in time of creation, it was 22 times stronger than it is today. So what that means is very, very few cosmic rays getting into the upper atmosphere to produce carbon-12. So that means carbon-12 is going to be building up in the atmosphere very, very slowly. Now, around the time of the flood, some studies have been made that show that there was a dramatic change in the Earth's magnetic field around about that time. So after that time, the amount of carbon-14, the rate of production of carbon-14 would go up dramatically. So we might have had something like, with a 10 to 20% difference, or factor of 10 to 20 difference in the strength of the magnetic field, we might have only had 5 to 10% of the carbon-14 in the atmosphere that we have today. So how about carbon-12 then? Well, here, let this represent the amount of carbon-12 in the atmosphere today. How much at creation? Who knows? However, we've observed that there is a large amount of coal buried all over the Earth. That speaks to a very large amount of vegetation that got buried during the flood to produce that coal. And that, in turn, speaks to a very large concentration of CO2 in the atmosphere to support all of that growth. We know, for example, that if you double the CO2 concentration, you will get about 41% more plant growth. This is important stuff for people who run greenhouses. They do this. They actually pump carbon dioxide into their greenhouses so they get more plant growth. All right, so could be more. There's obviously more carbon dioxide in the atmosphere, relatively speaking, than there is today. That means more carbon-12 in the atmosphere than there is today. But how much more? Well, there's a publication, a secular publication, that has examined rocks down through the geological column, and based on their chemistry, has made estimates of what the carbon dioxide ratio in the atmosphere probably was at the time those rocks were being formed. They're carbonate rocks, so the degree of which they would have carbonation in them would depend on how much carbonation there was in the ocean, for example, how much carbon dioxide was dissolved in the water. And they've done, what was stated in the report is that 500 million years ago, which is about the time of the Cambrian rock layer, carbon dioxide level was 20 times what it is today. During the Jurassic, which is supposedly about 158 million years ago, it was 4 to 5 times what it was today. And then approximately 49 million years ago, they say there was a very swift reduction. Now, if we were to suppose that at the start of the Cambrian that the Cambrian rock layer is the start of the flood, and I'll say now, there's a lot of discussion about where that is, actually. It may or may not be at the Cambrian, but let's take it there for now. If that was the start of the flood, then this would be around the middle of the flood somewhere. And this sounds like it's like immediately after the flood, when the vegetation was all growing back in and sucking carbon dioxide out of the atmosphere, right? So that all kind of fits with a flood scenario. But that means that back about the time of the flood, the carbon dioxide level in the atmosphere was about 20 times what it is today. Now, today it's about 400 parts per million, right? We're constantly reminded about that. And so that means that back in the time of, say, the start of the flood, back in the time when the Cambrian rocks were being deposited, it was about 0.8%, 800 parts per million. And that's less than 1%, which is still okay from a human health perspective. So it's not like Adam and Eve or all the people on the ark would have died from carbon dioxide poisoning. All right, it's still perfectly okay. But this, of course, if this is true, this will dramatically change that assumed ratio during the time the vegetation was and the animals were existing, were alive. Right? That changes that ratio, pre-flood, to somewhere around, if the 5 to 10% is true, and this 20% or 20 times is true, changes the ratio to something like this. So that means that fundamental assumption that's used in calculating radiocarbon ages, from a biblical perspective, is wrong. Well, actually, from a non-biblical perspective, is wrong. And in fact, they do have a carbon dioxide or a radiocarbon calibration curve that they use for things in the recent past that takes into account nuclear testing and all of that sort of stuff. But it doesn't change it very much. But this has a dramatic change to it. So all of those ages likely should be a whole lot smaller. In fact, if the numbers were such that the ratio was 0.004, which is kind of in the bracket, then the answer you would get for the ages of all of these things is about 4,500 years. Okay? Now, there's a very telling admission. It was at a conference quite some time ago, 1970, where a fellow who uses these dates pointed out that if a carbon-14 date supports their theory, that is, it gives them the answer that they want, that they expect, okay, so they know that this fossil is this old because of the rock layer, either because of the rock layer it's in, or because of the ages they know for the fossils above and below, or whatever the reason. If it supports that, they'll put it in the main text of their journal article. If it doesn't entirely contradict them, we put it in a footnote. People never read footnotes anyway, so it doesn't matter. All right? And if it's completely out of date, we just drop it. So when they get the right answer, they use it. When they get the wrong answer, they ignore it. That's actually got a term, two terms in science. One is confirmation bias. They only use the things that confirm their already existing bias, and they cherry pick the data to do so. All right, so summarizing all of that, it would seem none of the radiometric dating techniques are really all that reliable. Radiocarbon, in fact, provides evidence that the rock layers are pretty much the same age and a lot younger than we're led to believe. Now I'd like to talk about a different approach to radiometric dating, what I call radiogenic helium dating, and it uses zircon crystals. These are little wee tiny crystals. Well, some of them are tiny anyway, but they have a particular crystallographic characteristic, and that is when the crystal is forming, the crystal structure is such that uranium can be incorporated into the crystal, but lead can't. It has to do with the relative shapes and sizes of the crystal structure and the atoms of these two things. Okay, so this dating techniques makes use of the decay chain from uranium-238 to lead-206, and incorporates the assumption, based on the characteristics of the zircon crystal, that there will be no lead in it when the crystal is formed, but there could be a bunch of uranium. Now, when uranium decays to lead, it emits 8 alpha particles. And alpha particles are helium nuclei, and you can see those other little things that are coming off are electrons, and so these helium nuclei lob onto those electrons and become helium atoms. And helium is the smallest noble gas, and it doesn't form compounds with anything, and it leaks out of everything. How many people have bought helium-filled balloons too early? And they all go, and they're designed to keep helium in, right? Stuff that isn't designed to keep helium in leaks out. In fact, helium is used as a leak detector in a lot of vacuum equipment. So we have these zircon crystals with uranium atoms in them, and for every uranium atom that decays to lead, you get 8 helium atoms. So it looks like this, okay? We got a pile of uranium, one of those decays to lead, and we get 8 helium atoms. Now, because helium is slippery, it starts diffusing out of this helium crystal, so we get this kind of action. And then after some period of time, another one will decay, and so on and so on. Now, some scientists got some zircon crystals from Los Alamos National Laboratory that was drilling a very deep borehole in New Mexico. And they sent these zircon crystals away for analysis, and they got back something like this. They got back, there was a bunch of uranium, there was a bunch of lead, and based on the ratio of lead to uranium, they would calculate that the radiometric age of these crystals was 1.5 billion years. Now, based on the amount of lead that was present, you would expect to see this amount of helium. And that's how much helium would be produced with that much lead, 8 times the number of lead things. Then, given that the age was actually 1.5 billion years, you would expect most of that helium to have diffused out very long time. Helium's very slippery, so most of that would be gone. So you might expect that amount of helium to be left. What they actually observed in these crystals was a very large amount of helium present, up to half of what would have been produced by that number of lead atoms. So the scientist involved, who as it turns out, is Dr. Humphreys, who we talked about this morning. He did a calculation. He calculated the rate at which helium would diffuse through zircon based on two assumptions. One was that the crystals were, in fact, 1.5 billion years old, and the other one was based on the assumption that the crystals were, were just 6,000 years old, right? And you can see these are quite different. Now, they both appear on the same sheet of paper, but the scale on the left-hand side is logarithmic, so the difference is actually a factor of 100,000. It's not like they're just a few percentage difference. They're really different, which you understand. Like it's 6,000 years versus 1.5 billion years, so this is a big difference. Okay, so he did that calculation in 2000. Then in 2003, they got some more crystals, and they sent them away now for other analysis. Oh, I should point out that the reason that there's a line here is that these crystals came from different depths in the borehole, which means they were at different temperatures, which means that the rate of diffusion would have been different. And when it's hotter, it'll diffuse faster. So that's why we have these little curves. So then they were sent away, and they got some more crystals. They sent them away for similar measurements. Measurements that they got back were plotted on the same graph, and they came out here. You can see all the little circles for the data. They overlap exactly the creation model. They're 100,000 times different from the uniformitarian model. In fact, they did a calculation to get the best fit, and they got 5,681 plus or minus 2,000 years. Now here you can see a concrete example of the difference between accuracy and precision, or repeatability, or uncertainty, right? The accuracy is the difference between 5,681 and 6,000, which is the right answer, or maybe this is the right answer. The plus or minus 2,000 is the uncertainty. So it's kind of uncertain, but pretty accurate. Now, this suggests two possibilities. Either the diffusion rates have been dramatically lower in the past, or radioactive decay rates have been dramatically higher in the past. Well, they set about to see if they couldn't find some corroborating evidence for one or other of these. They got some other crystals, feldspar, normal rock crystals, from this same borehole, and they used a different dating technique that's called the Argon dating technique. So normally you have potassium in this feldspar, which will decay with that long half-life that we talked about before to argon-40, and it'll be trapped in the crystal. What they do for this is they make use of another isotope of potassium, potassium-39, which is a stable isotope. They put the rock in a nuclear reactor, radiate it with neutrons, and some of this potassium-39 produces argon-39. Now, argon-39 is also radioactive, and it decays with a half-life of 269 years. So as soon as they start producing it, some of it starts to decay. But if you do the rest of the experiment quickly enough, in a day or so, that 269 years really is of no significance. Then what they do is they measure this ratio, right? Much like you measure the ratio of carbon-14 to carbon-12 in a mass spectrometer, and then they calculate the age with a formula like this, okay? So they did this. This had been done with a particular sample of the feldspar crystal. And if you look at the argon-40 in particular, it would have a distribution like this inside the crystal. So it got formed uniformly throughout the crystal, but then over time, the stuff around the edges would leak out. And so that's surface leakage since it was formed. Then when they put it in the reactor and irradiated it, they would produce argon-39, again, throughout the crystal, but some of it around the edges would leak out since the experiment was formed. So then what they do is they basically vaporize the crystal incrementally, so from the outside in, heating it up to boil off the gas, and they measure the ratio of argon-39 to argon-40, and they get a graph like this. And based on that, they calculate an argon-argon age of 1.16. So significantly less than the zircon crystals, which are embedded in the same rock, which seems a little odd, but same order of magnitude, I guess. But you can also look at the amount of argon-40 that's retained versus the amount of argon-40 that is lost by diffusion, and using the known diffusion rate of argon through feldspar, calculate an argon diffusion age, which turns out to be almost the same as the age of the zircon crystals. So we have some supporting evidence that the age is only 6,000 years old. And since we're using two different gases and two different materials, it would seem like it's not the diffusion that's being different, it's the radiometric decay rate that is different. So let's look at that. Here is the implications of that. Here is the standard uniformitarian assumption for radiometric decay of uranium. So you start out with an amount 1 here, and over, what is what I got there, 4.5 billion years, it would decay according to that curve down to the present, in which case we would have approximately 50%, 49% of what we started with. Now, 450 years earlier, that ratio would be almost the same, and 1,500 years before that, it would still be almost the same, okay? You can see there are slight differences there in the last digit, but that's it. Now, suppose you had a history that looked like this. Okay, here's the present, and there's the given ratio in 4,500 years ago and 4,900 years ago. Now, the blue line, which looks flat here, because we're only looking at a very tiny time frame, but it actually goes up. If you go back 4.5 billion years, it'll go back up to 1. But suppose 6,000 years ago, you started at 1. You had a normal decay rate for some period of time. Now, I've picked about 1,500 years. And then you had a very dramatic increase in the decay rate down to that same fraction. And then after that, you had the normal decay rate. What would turn out from that is that all through this region, where you're simply measuring isotopic abundances, the ratio of different isotopes in the material, the observations would be exactly the same regardless of the history. So there's no way you can tell just from those measurements what the history actually is. Right? But we have measurements that indicate that the history is that one. So, radiometric dating, in summary, depends on a bunch of assumptions that have been demonstrated to be unreliable. It's uncalibrated, and I think that's really significant. It gives ages that don't agree with known ages. It gives ages that don't agree with each other when they're supposed to be measuring the same thing. And then we have carbon-14 in coal, diamonds, dinosaur bones, and charred wood, which contradicts the assertion that they are millions and billions of years old. And in fact, the difference in the calculated ages, based on the normal assumptions, can be easily explained within the biblical expectations. And then we have we have a helium diffusion measurement in zircon and the argon diffusion measurement in feldspar that, again, give ages that are consistent with the biblical history. And both of those use different physical property than normal radiometric decay, and on two different elements. So, all different materials. So, as I said to start, no, radiometric dating doesn't prove that the Earth is billions of years old. First, because it doesn't, and then, in fact, because it provides empirical evidence that contradicts the old age assumption. Now, those of you who were here this morning have already seen this. Now, how many of you remember this? And why I show this? Why do I show this? To remind you that in order to review, you have to have some resources to review. And this is one of our best resources. And in order to be equipped to answer questions, this is a really excellent resource. And in order to be able to refute arguments, this is also an excellent resource. And you can see it actually has a chapter on radiometric dating right there. And then there are a number of other resources out there that have to do with ages of things and radiometric dating in particular. This is perhaps the definitive work. Well, the definitive work actually isn't available anymore, but this is a summary of the definitive work. Comes in book form and DVD form. This is also an excellent book. I'm not sure we have any on the table. And then there's the DVD called The Age of the Earth. The important thing, again, as I said last time around, is we need to be equipped with information so that whenever we get questions or hear arguments, we're equipped to be able to deal with them. So thank you very much for your attention. Do we want to take questions? Oh, good. No questions. Oh, maybe we could turn it around. I could ask the questions. Remember I said this morning there was going to be a test? We could have a test on this morning's talk. How about that be? No? Okay. Well, then I guess we're what? Got a half-hour break?